Mr. Rocco, Servedio, who tell us about pseudorandom generators from pseudorandom multi-switching.
Okay, thanks, Raghu. This is joint work with Leon, who just spoke to you, and I'm going to piggyback off of a couple of things that he said. I want to thank the organizers for inviting me to this workshop. I tried to really live up to the title by proving and using pseudorandomness. I have pseudorandomness twice in the title, and I guess once is proving and once is using. So hopefully it fits the mission. By this point in the workshop, I think we're all pretty familiar with this notion of pseudorandom generators, so I'll go through this first slide very quickly. We have some circuit class that we're interested in, and a PRG for the class is just an efficient deterministic algorithm that stretches short, truly random strings to pseudorandom strings, which can fool all the circuits in the class. So you've got some kind of r-bit seed. I've got a pointer here. The generator is deterministic. It gives you an n-bit output drawn from this distribution, which successfully fools every function in the class. Whatever your circuit is, the difference in expectations or acceptance probabilities is at most epsilon. OK. So we're in California. We're dreaming. We wish that we had PRGs for the class of all polynomial-sized circuits. But I think all of us know that this is not right around the corner, right? As Leon mentioned, if you have PRGs against a circuit class, this means you have circuit lower bounds against the class. And in fact, you even have average case lower bounds, correlation bounds. OK? So if we're interested in staying within the realm of sort of unconditional pseudorandomness, and we don't expect to prove new circuit lower bounds or correlation bounds, then we can only really hope for PRGs against circuit classes where we have these things already, circuit lower bounds or correlation bounds. And that's what this talk will be about. It's focusing on two specific classes where we have circuit lower bounds and correlation bounds. We really are going to be trying to achieve, and we will be achieving, kind of the best PRGs we could hope for, given the state of the art on these harder problems, or these problems. Okay? So I couldn't decide between two introductions. One was sort of oriented around results, and one was oriented around techniques. I decided I'd give you both introductions, and if there's any time left, we'll see what happens. So the results-oriented introduction, if you want to sort of put this work in a nutshell or a bumper sticker, we give essentially the best possible PRGs for two well-studied classes of Boolean functions. The best possible in the sense that improving our results would require getting better circuit lower bounds or correlation bounds. Okay? The two classes are constant depth circuits and sparse GF2 polynomials, and I'll start by telling you about the results for constant depth circuits. So this is just AC0. We've been talking about this on and off throughout the workshop, right? We all know what these circuits are, and NOR gates. We measure the complexity of the circuit, the size, just the number of gates, and the depth is the depth. What do we know about lower bounds for these constant depth circuits, which again are sort of a barrier for pseudorandom generators? Well, the strongest known circuit lower bounds are basically exponential in n to the 1 over the depth minus 1. So we have like 2 to the root n circuit lower bounds for depth 3 circuits, so on and so forth. Given this, what can you hope for? Well, you sort of invert this easy argument that tells you about PRGs implying circuit lower bounds. The best PRGs we could expect without kind of breaking through this barrier, which like Leon said is 30 years old, would have seed length something like this. Log of the circuit size with an exponent of d minus 1, and just log 1 over epsilon in terms of the error parameter for the PRG. Okay, so this is what one could reasonably, or without hoping for a real breakthrough, try to achieve for PRGs for AC0. Okay, so there's been a long line of work on PRGs for AC0. Leon mentioned this Itai-Vigdersen work, which got the whole ball rolling. We've talked on and off about the Nissan's generator, which was, sorry, not Nissan's generator. This is basically the Nissan-Vigdersen paradigm, so on and so forth. A line of results leading up to something quite recently this year, or this past year, by Harsha and Srinivasan. Let me just highlight a couple of quantitative aspects of these different results. So Luca's PRG, the Trevisan-Schrey pseudorandom generator for AC0, for the first time got the right dependence on the size parameter. Right? If you look at the previous works, we had something like maybe log to the 2d or log to the d squared or something like that. Luca got log to the 1.0 times d. So it's possible to get the right dependence on size. This very recent paper by Harsha and Srinivasan showed for the first time that you can get the right dependence on the error parameter. Just log 1 over epsilon as opposed to, if you look at all the other things, the 1 over epsilon is in like a log to the d or a log to the 2d or something like that. Okay? So you can probably guess where this next slide is going. What we do is we manage to sort of get the best of both worlds of these two previous generators. So we're not getting exactly log to the d minus 1. It's log to the d plus some absolute constant. But we have kind of the right dependence on m. We're getting the right bound up to the additive constant in the exponent on the log and the right dependence on epsilon. And again, this is best possible, but that's modulo current circuit lower bounds. Okay?
And that's really the product, not the sum of these two, for the best possible.
Yeah, I think
Not
if
sure.
epsilon is inverse polynomial, you need to lose another log. Because there is this reduction from correlation bounds for that d to lower bounds for that d plus 1.
Yes. So you're saying it is the product.
Yeah.
Okay.
Yeah, epsilon is also important.
I take Nico's word for it.
Plus log 1 over epsilon for DNS.
I think if you could add, you get something new circuit lower bounds.
If you get a plus.
Yeah, I think so.
So if epsilon is inverse polynomial, the right bound has to be log to the d.
D,
Right,
I
right,
see.
right.
So there is a bit of
Okay. Good.
leeway of another one.
Okay, so that's, we're still in the results-oriented introduction. That's the result for AC0 circuits. We also can say similar kinds of things for sparse F2 polynomials. So just a little picture. These are just neither more nor less than parity of AND gates. And we measure the size by the number of AND gates or the number of monomials in the polynomial. Here we don't have a lower bound as our barrier. It's trivial to have lower bounds, right? Every function has a unique representation as an F2 polynomial. But the correlation bounds are a barrier, right? It's sort of this long-standing challenge. There are people who you could make very happy by giving correlation bounds against F2 polynomials of degree more than log n. Okay, and if you think about it, degree log n over n variables, that's n to the log n possible monomials. So we don't know correlation bounds once s gets to n to the log n. If you invert n to the log n, it turns out that sort of the best PRG we could hope for would have seed length 2 to the square root log of the sparsity. Okay, and again, with this log 1 over epsilon, we'd like, this is kind of, the bench, this would be sort of the gold standard given current correlation bounds for these F2 polynomials. So again, you probably can guess where this is going. In previous work, this is Luby, Velikovic, Vigderson. They were able to get the right dependence, modulo the correlation bounds on S, but the epsilon is not where we want it to be. It's hanging out up in the exponent instead of being down below. There was previous work on a related class, so low degree GF2 polynomials instead of sparse GF2 polynomials, where they were able to get the epsilon in the right place, like a log 1 over epsilon dependence down in the bottom. And what do? We sort of put these things together, and we managed to do it right, with this correct dependence on square root log s in the exponent, and log 1 over epsilon, the best possible dependence on epsilon, down in the base. And I didn't really call attention to this earlier, but you maybe noticed over on the right-hand side of the analogous slide for AC0, sort of this highlighted business of the techniques. The new technique that we'll be talking about to get these results is de-randomizing a multi-switching lemma. And I didn't mention this a couple slides back, but the key technique of Luca's earlier work, his PRG, was de-randomizing a non-multi-switching lemma, sort of a vanilla switching lemma. Okay, so that's going to be sort of the delta of what we do, and if I get to any technical content, that'll be what the technical content's about. Okay, good. So that was the first introduction. Now for a techniques-oriented introduction, just saying the same thing I said 1 second ago, the main sort of technical contribution that we make is coming up with a way to have a pseudo-random variant of these multi-switching lemmas. And throughout the talk, I think I'm going to be mostly referencing Hastad's recent multi-switching lemma from 2014, but an essentially equivalent multi-switching lemma was obtained by Impagliazzo, Matthews, and Pittori. I think you could sort of use them indistinguishably in the arguments, but just for concreteness, I'll be referring to Hastad's stuff, okay? Good. So I'll go through this, the basics very quickly. We all know and we all saw from Leong's talk, what is a restriction of a function? It's just a way of fixing some of the coordinates of the function to constants and leaving other coordinates alive. The standard restrictions that people most commonly think about are truly random restrictions, these quote-unquote RP restrictions, where coordinate-wise independently, you let each variable survive with probability p and fix it uniformly otherwise, okay? So those are restrictions. What do switching lemmas say? They're just statements which basically say that DNFs switch to CNFs when you hit them with a random restriction or vice versa. In fact, switching lemmas tell you a little bit more. Sort of the most famous switching lemma is Johann's switching lemma from the mid-'80s, which says if you have a k-CNF and you want to sort of analyze what happens when you hit it with a random restriction, in fact, it collapses to a shallow decision tree of some depth with an exponentially decreasing probability. Okay? And this decision tree, of course, you can think of as either a DNF or a CNF. So it gives you the kind of statement about switching from DNFs to CNFs and vice versa.
Sorry, can you remind the restrictions? Is it just restrictions to constants?
Coordinate-wise independent, everybody stays alive with probability p, otherwise uniform constant.
Okay.
Yes. Right. Okay. And Leon touched on this too in his talk. Sort of a nice thing about this bound is if you think about, say, a polynomial size CNF formula, this starts to kick in. It tells you something when p is quite large. It can be as big as, say, 1 over 10 log n or something like that. Think of k as being log n if the CNF is polynomial size, right? And you'll have something like a half, which then decreases exponentially in the depth of the decision tree t. Okay, so it's a nice thing about the Hastad switching lemma is that it gives you sort of a meaningful statement in this context for large p, p being 1 over log n. Okay. Well, like Liang said, we're not going to be making much hay if you deal with truly random restrictions in the context of de-randomization. So we have to think about pseudo-random restrictions, right? And these are, again, just some distribution over restrictions that's more randomness efficient. Somehow you don't have to toss so many coins to generate one of them. Okay? Itai and Vigderson were already using pseudo-random switching lemmas to get PRG results. These were sort of the first bullets on the slides I showed you earlier. And Luca and Tonka Shrey, I guess, gave a essentially optimal pseudo-random switching lemma. They were able to de-randomize the switching lemma by sort of this very clever approach of fooling the proof, and I'll talk more about that later. The sense in which I'm saying it's optimal here is that you can take kind of the same parameters and get the same conclusion as the truly random switching lemma. You can handle a p as large as like 1 over log n, the same way the genuine switching lemma, the original one, could. And being able to handle such a large p is one ingredient that led him to this good seed length in his PRG for AC0. Okay? And there are other works, which were mentioned earlier, giving, in Liang's talk, giving pseudorandom generators via pseudorandom switching lemmas. Okay. So in terms of techniques, what do we do? It's maybe a little bit analogous to Michael's talk earlier today when he was saying, you sort of take these components of Nissan's argument and you do them in this new framework. We're going to be working quite similarly to what Luca did, but instead of de-randomizing the switching lemma, right, we're going to be de-randomizing these recent multi-switching lemmas, or in particular, this recent multi-switching lemma of Hastad. Okay, so I got to tell you a little bit about what is this multi-switching lemma and so on if we go on in this talk, which I guess we can given the time. So yeah, this is not, it's not so simple as you prove this sort of pseudorandom multi-switching lemma and you're done. There are other ingredients which have to come into play in order to get the actual results. In particular, we use this Itai-Vigderson sort of iterative chunk-by-chunk kind of framework, basically the kind of thing Liang was talking about earlier. And for both our results, it's absolutely crucial that we have this Harsha Srinivasan PRG from last year. Remember, these were the guys who were first able to get just a log 1 over epsilon dependence on the seed length, and we explicitly use that. We rely on that in a crucial way. Okay, and there's some other ingredients for the F2 polynomials as well, and so on. So just to remind you, yeah, most of the rest of the talk, I guess, will be about the de-randomized, the pseudorandom multi-switching lemma. But just to sort of say something about the other aspects of the work, I'll have one slide here just reminding you, hopefully it brings back fond memories from before the coffee break from Liang's talk. You can see it was stolen more or less from his kind of slides in terms of the visuals. Just a quick idea of like how does the pseudorandom switching lemma help us get a PRG, right? How does it work? Well, it's the kind of thing we saw before. A pseudorandom switching lemma, we have some pseudo-random way of filling in the stars, okay? And we fill in the non-stars in a truly random way. A pseudorandom switching lemma tells us that such a restriction collapses, say, a small CNF to, or a small width CNF to a shallow decision tree with very high probability. Okay, so it's much the same kind of thing we saw in the search context, but a little different. We can't sort of prune the search tree. We have to expand out the search tree at all levels in order to get a pseudorandom generator. So we cycle through all the different choices of a pseudorandom set of stars. We cycle through all the possible assignments to the variables in the chosen set of stars, assigning, according to some pseudorandom distribution that fools the functions that come out of the pseudorandom switching lemma, right? So we're sort of trying this set, trying this set, trying this set, and for each of these sets, we try all the possible settings according to the pseudorandom distribution that fools decision trees. And then we have this branching, right? For each one of these choices, we proceed to the next stage. We fixed, these bits in some way. Now we're going to go on in the second stage. We'll fix another block of bits. Very similar in spirit to what we saw Liang doing earlier. Okay, and very similar to what we saw Liang doing in each single stage. So this is a cartoon of one stage. In each single stage, we fill in a pre-fraction of the coordinates. Okay. And whereas Liang, in his setting, you just sort of went for, think of it as like 1 over p or 1 over p log n, many stages to do this approximate counting, and it wasn't an expensive thing. Even if we had to do n stages, that's just like a multiplicative factor of n in the running time. Now we're branching. Now we have this branching factor. So we really do want to take p to be very large, right? The more stages we have to do of this, the deeper our tree is, and the worse, sort of the parameters of our overall PRG are going to be. So this is why sort of peeking back and also peeking forward, it's very useful to have something like Luca's pseudo-random version of Hastad's switching lemma where we can take p to be quite large. Okay, that leads to strong parameters. Good. Okay, so we're done with both introductions. Do I have any? How much time do I have left? 15 minutes, 14 minutes? Okay.
40, yeah.
Okay, so I can talk a little more. And the rest of the talk, I'm going to just focus for concreteness on AC0. I'll remind you of sort of the stuff about the switching lemma and basics about the multi-switching lemma, which may be a little less familiar. We'll sort of give a quick overview of how Luca was able to use a de-randomized version of the switching lemma in order to, how he was sort of able to come up with a de-randomized version of the switching lemma by fooling the proof of Hofstade's switching lemma to get his pseudorandom switching lemma. And I'll sketch at a very high level how we're able to do something analogous, fool the proof of the multi-switching lemma to come up with a pseudorandom multi-switching lemma, which turns out to have the kind of parameters which give us the results I said earlier. Okay. So again, switching lemmas and multi-switching lemmas. We saw already sort of a written out version of Hofstade's switching lemma. It tells us that when you hit a CNF with a random restriction, a truly random restriction, it's very, very likely to collapse to a shallow decision tree. It's very likely that some shallow decision tree computes it. Okay? Good. And typically, we're used to thinking about this lemma, applying it in the context of AC0 circuits, where we don't just do this once, we do it a whole bunch of times. We have maybe D or D-1 or D-2 stages of doing this, and within each stage, we do it many times. You have something like, if it's a size M circuit, you maybe apply it to as many as M different depth 2 circuits, 2 levels up from the bottom. Okay, so if you want to think about how does the switching lemma play out in this context of using it to do depth reduction, what ends up happening is that essentially you need the error, right, or rather I should say the failure probability of the switching lemma to be something like epsilon over M. If it's something like epsilon over M, then a union bound over the potentially M different applications within a given level will let you get something like an epsilon failure probability out overall. But if you're doing it where the failure probability is something like epsilon over M for a single thing, this means your exponent is going to be something like log M over epsilon. Okay, and if your exponent is log M over epsilon after the first stage, well, at the next stage, now when you apply the switching lemma, you're applying it to like a log M over epsilon with CNF. Epsilon has kind of crept into the picture. At the next stage, the bottom fan-in has this log M over epsilon. It has a dependence on epsilon. And so your subsequent applications of the switching lemma, the second, third, fourth time, you're always going to have a dependence on epsilon and P. In particular, P after D applications, sort of hitting it again and again and again, it'll be something like P will be something like 1 over log M over epsilon to the D. So this is not so good, right? We don't want to have something like a log 1 over epsilon to the D. We want to end up at the end of the day with just a log 1 over epsilon. Okay, so this is just kind of a little hand waving of why the original switching lemma, even in the truly random version, is not quite tailored for our ultimate purposes of having this optimal epsilon dependence. Good, okay. So that's the original switching lemma. Just the last couple of years, there's been this really cool work on developing these so-called multi-switching lemmas. These are like variants, generalizations of switching lemmas, which can analyze many CNFs at once. You look at a random restriction, and you say something good happens to a whole collection of CNFs. So to understand what these say, we need this notion of a common partial decision tree. And it's a pretty straightforward notion. You've got a bunch of Boolean functions. A decision tree is a common L partial decision tree for this collection of Boolean functions. If every function in the collection is expressible as just that decision tree with a little bit of extra stuff at the bottom, in particular, depth L decision trees augmenting it at the bottom. So I think a picture helps. If this is my family of functions, F1, F2 through Fm, a common L partial decision tree is just a decision tree T such that I can write F1 as this decision tree with little depth L decision trees glued onto the bottom. Right, it's common to all of them. F2, the same tree T with different depth L decision trees glued on at the bottom. Okay, so it sort of does the brunt of the work, and you have to do a little bit of cleanup. You could think of it as like the different depth L trees down at the bottom. Okay, so this is this notion of a common partial decision tree for a family of functions. The multi-switching lemma, and again, I'm sort of referring to Hofstade's version here, but there's an equivalent version of Pagliazzo et al. The multi-switching lemma says what? It says, well, if you have a family of CNFs, and you hit that family with a random restriction, this is just saying the worst CNF, the worst function in the family, after a random restriction, the probability that any of them don't have a common partial decision tree of with this log 2m depth for the extra parts you need hanging off the bottom, that's exponentially small. Okay, it goes down very fast. So you can think about applying this multi-switching lemma in a context of AC0 circuits, and something much nicer happens in terms of the depth reduction now. Okay, if you look at sort of the picture that comes out, you have an AC0 circuit originally, you hit it with the restriction. What this says is that you're very likely, with all but epsilon probability, you end up as a decision tree. The depth of this decision tree now is where the epsilon is hanging out. The log m over epsilon is the depth of this tree. down at the bottom, you have these circuits C1, C2, and so on. You've done depth reduction, and their bottom fan-in, crucially, doesn't have any dependence on epsilon. The bottom fan-in depends only on m. Okay, and that's important because it means you can do it again. You can hit it with another random restriction. You'll get down to sort of the first tree T1, a second tree T2, and then circuits of depth d minus 2, and so on, but you're never having an epsilon in the picture for the bottom fan-in of these guys. Okay, so in particular, you run this d times, and your overall final value of p will have no dependence on epsilon. Right, and that's a good thing, because we saw that we're going to pay something like this 1 over p as in the overall pseudorandom generator. Okay? So again, this is just kind of hinting at why the multi-switching lemma is maybe a useful thing for our sort of context. Good.
What was the motivation for that?
These guys were trying to take optimal correlation bounds for AC0 circuits. Yeah, or I guess Hastad was going for correlation bounds in the other work. If Russell is here, he can tell us the motivation. Was it counting or satisfy? Oh, like non-trivial satisfiability algorithms for AC0. Okay. Okay. So with Luca in the audience, let me try to quickly give a recap of how we thought of Trevisan-Schrey's working. For this, to explain this, I need to give you a little bit of setup. It feels like a kind of wonky notational thing, but I think we sort of need this. Or actually, that'll be the next slide, yeah. So, yeah, OK. Here's setup for how Luca is able to prove his pseudorandom switching lemma. This is maybe the most important part of any of the slides. There's this notion of a canonical decision tree. Okay, for a given Boolean, for a given, let's say, CNF formula, we have this notion of a canonical decision tree. Okay, it's like a particular way of computing the decision tree as computing the CNF as a decision tree, and it's just the natural way that, given a CNF formula, you would compute a decision tree, right? You look at your CNF formula, and if it's constant 0 or the constant 1, you throw down 0 or 1. That's the decision tree. Otherwise, you've got a list of clauses. There's like some fixed ordering. You look at the first sort of non-trivial clause that isn't identically 1. Query all its variables is your way of building a tree, right? You've done some substitution, so you can simplify the other clauses now, and recurse. At each of these leaves, go on and build the decision tree for the remaining sub-CNF that's induced by that restriction so far. Okay, so a very simple kind of standard way of cooking up a decision tree for a CNF. It's the first thing you'd think of if I gave you a CNF and said, write this as a decision tree. Okay. So if you look at what the switching lemma actually does, the way we stated it earlier is a little weaker than what it really gives you. We stated it before as saying, if you have a CNF and you hit it with a random restriction, it's very likely that it collapses to some shallow decision tree. What Hastad's proof actually establishes is that if you hit a CNF with a random restriction, it's actually extremely likely that this decision tree, the canonical decision tree, this process of building a decision tree on the restricted CNF gives you a very shallow tree. Okay, and this is crucial for Luca's arguments. He really exploits the computational simplicity of this decision tree construction procedure. The fact that this canonical decision tree is built in a very sort of simple and straightforward way, given the function that you're trying to build the tree for.
What, do you mean simplicity or computational simplicity?
I don't know. This is a simple.
What is the word computation? What is the adjective computational mean?
Descriptional simplicity. It's just the fact that you can look at this procedure and you can analyze this procedure. You can sort of talk about what this procedure needs to do.
But you don't mean like you need to understand the computational complexity of going from the DNF to the decision tree.
And this is maybe a semantic discussion,
Okay.
which let's take it offline.
Yeah.
Okay. Okay. So to sort of instantiate this, show you this in a little bit more detail, I need, again, kind of a wonky technical thing about, encoding restrictions as bit strings, right? It's sort of something we have to do for this to make sense. So what's a restriction? It's a string of zeros, ones, and stars, okay? If we want to talk about, sort of analyzing restrictions in our kind of framework, we need to think of restrictions actually as, bit strings, okay? So there are many ways you can do this. This is a very natural way of doing it. I want to think about a 0, 1 star string as, I'm going to interpret a sort of a binary matrix, a matrix of bits, as a 0, 1 star string in this natural kind of way, right? I look at these first log 1 over p many rows of the matrix, and if I see that it's all ones in a given row, which happens with probability p for each row, then I take the last row and I spit out that bit. Then I actually give you a bit value, right? So here I have 0, here I have 1 because the last row is 1. Here again, I have 2 columns of all ones. I have 1 and 0, so I get 1 and 0 out for the corresponding restriction. And for everything else, in all the columns where I don't have all ones, in other words, a 1 minus p fraction of them, I just put down a star. Okay, so it's just sort of an example of simple procedure by means of which you can kind of go from a binary matrix like this to a restriction. So now we can notice something very simple. If I have a uniform random binary matrix, right, well, then the probability for each coordinate independently that I'm going to get the bit value in the last row is just going to be p. So a uniform random binary matrix, right, would correspond to a truly random restriction. On the other hand, if I have some kind of way of constructing pseudo-random bit matrices, right, pseudo-random elements of the space of all possibilities up here, that will in turn induce some distribution, some pseudo-random distribution over restrictions. Okay, and that's what we want. We want some kind of randomness efficient distribution over restrictions, because that's what we're going to be able to deal with. So this is kind of the crucial claim, I think, in Luca's work. It says what? It says that kind of since this canonical decision tree construction is so simple, it's possible to show actually that there's a very simple circuit, a depth 3 circuit, which outputs 1, given as input the description, the sort of bit string describing a restriction, it outputs 1 if and only if that restriction is a bad restriction, a restriction which leads the canonical decision tree to have large depth. Okay? This is really just an OR, just a glimpse a little bit behind the curtain. This depth 3 circuit is an OR over all possible paths that could be long paths in a decision tree. Okay? So we just have, again, in pictures, some very simple circuit, a depth 3 circuit here, which given an encoding of a restriction, it outputs 1 if and only if the restriction sort of contributes to the failure event of the switching lemma. Okay? And that's good because it tells us, hey, you don't need a truly random distribution over restrictions. It's enough to have a pseudo-random distribution that fools depth 3 circuits. Depth 3 circuits are sort of all that you've got to fool in order to be able to make this go through. Okay? So Luca exploits that. This is sort of a technical, I apologize, it's so technical, just read the highlighted stuff. His kind of main lemma says if you have any distribution that fools these depth 2 circuits corresponding, it's the technicality, depth 2 versus depth 3, corresponding to these deep paths in the decision tree, a distribution, a pseudo-random distribution over encodings of restrictions like that suffices to give you a Hastad switching lemma kind of conclusion. You can see we're exponential in t here. And so you can really plug in any kind of pseudo-random distribution over restrictions that satisfies this fairly mild property of fooling depth 2 circuits. It happens to be is all you need. Okay? So you do this d times. This is like one level of depth reduction. You do it d times, and you get depth reduction for an AC0 depth d circuit. Okay? So this was kind of a high-level overview of Luca's stuff. In the last minute or two, I'll just sketch very, very quickly our pseudo-random multi-switching lemma, which does something analogous, but we have to do it now for the multi-switching lemma instead of the switching lemma. So it's a lot of fun. If you want kind of an analogy to walk us through this, right, when we first talked about the switching lemma, we said, hey, the probability that your restricted function isn't computed by some small decision tree is extremely small. Your restricted function is probably computed by some very small shallow decision tree. But then the real deal, right, I'm doing it in this order, yeah. So this is for the original switching lemma, right? Probably there's some shallow decision tree which computes your restricted function. The multi-switching lemma, the way we described that a couple of slides ago, was saying, hey, if you've got a collection of these CNFs, then with very high probability, probably there's some shallow common partial decision tree that works for those guys. Okay, but we saw then that in fact, what Hastad switching lemma really gives us, and what Luca's argument exploits, is the fact that it's not just that there's some decision tree, right, which works, which is a shallow decision tree for the restricted CNF. There's actually this particular one, this computationally simple one, this canonical decision tree. Probably that is extremely shallow. And similarly, we need something exactly analogous. You can think of it as a variant of Hastad's multi-switching lemma, which says that there's some canonical common partial decision tree, some like concrete one that has an explicit description of how you come up with it, given the family of CNFs, which gives you a shallow common partial decision tree for a family of CNFs. So what is this canonical common partial decision tree? It has some definition. I encourage you not to read the definition, but just at a high level, intuitively, it's the kind of thing you would think. It's some way of plowing through the CNFs, one after the other, trying to build a decision tree as you go along. It's some well-specified way of cooking up the decision tree. Okay? And so we do something entirely analogous, very closely analogous to what Luca did. We have to analyze now this canonical common decision tree construction procedure, which you could see is more involved than the original just canonical decision tree construction procedure. But we're able to come to a similar kind of conclusion at the cost of one extra unit of depth. Okay? Instead of a depth 3 circuit, it turns out that now you have a depth 4 circuit, which recognizes bad restrictions, outputs 1 if and only if the canonical partial decision tree turns out to be deep. Okay? And there's something crucial here. The crucial thing will be on the next slide. So this is very much as before. We don't need to have true randomness for our underlying encoding of restrictions. It's enough to have a pseudorandom distribution that fools sort of the circuit that does this recognition. Right? Enough to have a pseudorandom distribution that fools this depth 4 circuit. Okay? So this is where, crucially, you're wondering maybe where Harsha and Srinivasan's log 1 over epsilon seed length PRG going to come in. This is absolutely where that comes in. So, right, this is sort of analogous to Luca's earlier statement. As long as you have a distribution that fools these depth 3 circuits, okay, then you'll get a conclusion similar in spirit, right, the same kind of quantitative thing, exponential in t everywhere. You'll be able to, then you get that the canonical L common partial decision tree, the probability that that is deeper than some t is inverse exponential in t. So this is exactly the kind of thing you want, but you've got to be able to fool this class of depth 3 circuits. Right? If we want our overall seed length to be just logarithmic in 1 over epsilon, you've got to be able to fool depth 3 circuits with a log 1 over epsilon seed length. But fortunately, thanks to Harsha and Srinivasan, this is exactly the technology they gave us. Right? They had a pseudorandom generator, if you recall from earlier, which I guess now the D that we would be plugging in for them is 3, right? Because we're just fooling these depth 3 circuits. So we have, this is just some absolute constant. I guess it's 9 or maybe a little bit larger than 9. But the dependence on 1 over epsilon is just a single log 1 over epsilon. Okay, and so that's how we're sort of able to get an overall dependence of log 1 over epsilon in our construction. Okay. So the takeaway, I think I'm out of time, is that there's a techniques-oriented takeaway and a results-oriented takeaway. The technique was developing a pseudo-random analog of the with multi-switching, the pseudo-random analog for multi-switching lemmas of Luca's pseudorandom, regular switching lemma. And by using that together with this Itai-Vigderson approach, and Harsha Srinivasan played a role, we're able to get these essentially optimal pseudorandom generators for AC0 and for sparse F2 polynomials, where you're not going to really be able to improve the parameters unless you can get some kind of very strong and exciting new results for correlation bounds or circuit lower bounds. Okay, so I think that's it. Thank you.
So maybe a high-level question. So you're kind of saying that a PRG implies kind of obviously a circuit low bound, or something like that, with a particular seed length, and kind of implicitly by working hard on a case-by-case basis, you can go in the reverse direction. Is there any hope to say something general?
Yeah, so I think it depends on how finely you want to slice the onion, right? Something like the Nissan-Vigderson generator is, you could think of it as like a generic way of going from correlation bounds to circuit lower bounds, but you're not going to get, really these like exactly matching parameters. Harsha and Srinivasan have a nice explanation of this. I think for a lot of classes like AC0, for I think sparse F2 polynomials and other things, you're not going to get better, for instance, than like a log squared 1 over epsilon dependence on the seed length. And it doesn't seem like there's a way to get better than like a log to the 2D dependence on the size for AC0 and so on. So, that is something like a general, somewhat general, tool to go in the other direction, but it's not maybe going to be enough to get you really the sharpest results you could hope for. Yeah. One phrase which I didn't use in this talk, but which maybe one could use in this context is like you've got some sort of computational hardness from these, you've got some hardness from these circuit lower bounds or correlation bounds, and you want to sort of convert all of it into pseudorandomness and get like the best pseudorandomness, the optimal parameters out that you could hope for. So that's sort of, with our approach, it seems you have to put these bunch of different ingredients together for that.